This is Unit 8, Video 2. We're going to continue talking about solutions and how we make solutions. So this slide asks the question, how can you dissolve a solid faster in a solution? So pretend you have a big crystal of something. So maybe a big crystal of your favorite ionic compound, maybe a copper sulfate. If you want to make this dissolve, it'll take a little bit, but you can speed the process up. And some of these are just logically understandable, pretty obvious. You can cut this crystal into small pieces. Essentially what you're going to do, you're going to powder it, make it into a powder. And that will definitely make it dissolve faster. Now what you're doing there is you're actually increasing the surface area. Because the solvation process requires molecules, say water molecules, to come along and bond with the solute. When you have a big crystal, all you have is the surface area on the outside. Water molecules can only approach this substance from the outside. But when you powder it, now you expose the inside to water molecules, so it dissolves much faster. That's why we like to use mortar and pestle to crush our substance here before we dissolve it. Once it's crushed, it just goes into solution instantly. You can also agitate the solution, which makes sense. That allows you to move around the solvent and make it come into contact with the solute method. So just do a little shaking, a little stirring. And then we can also increase the energy. We can add some heat. And most substances, as you increase the temperature, they'll dissolve faster. And that's because the molecules are moving around faster, so they'll find each other faster. So hopefully this is very logically easy to get at. Not too bad. Now, this may be a little bit new. We can classify solutions as saturated or unsaturated. So once you've made the solution, if the solution has the maximum amount of solute, it can't hold any more, then it's called saturated. The word saturated just means filled with, completely full. So any more you add will fall to the bottom. So if you have a saturated solution of some sort of salt, if you add a few more particles of that salt, it'll just end up at the bottom. It will not dissolve. It's reached its limit. But an unsaturated solution is not yet full, so it can hold more. If you add more, more will dissolve. Hopefully that makes sense. There is a type of solution called a supersaturated solution, and this is a fun one I'd like to talk about in a little more detail. And a supersaturated solution contains more dissolved solute than the solvent can handle. Now we just set up here that once it's reached the maximum, it's called a saturated solution, right here. And how can you go beyond its maximum, beyond its limit? Well, the way you do it is use heat. If you heat up a solution, more can dissolve. And then you cool it back down. And interestingly enough, it will retain or remain in solution if you do it kind of carefully and slowly. And there's some fun to be had with this. So an example of a home type experiment is the making of rock crystals, rock candy. I don't know if you've made sugar candy or sugar rock candy. What you do is you dissolve a lot of sugar in hot water. You put the water on the stove, get it to boiling, and it can actually go quite a bit above the boiling point because a solution has a higher boiling point. So you can get quite a bit of sugar dissolved. You're going to be running it maybe quite a bit above boiling point. So you can have a lot of sugar dissolved in there. And then what you do is you pour off the dissolved portion and leave the sugar behind. Don't let your solution have any sugar in it. And then put it in a container. Pour it in a container. You can put some food coloring in it if you want it to have a color. And just let it sit out. And slowly the solution will begin to crystallize because water will evaporate, reducing the amount of solvent further, so the solute will have no choice but to come out of solution. If you hang a little string on it, you can actually allow the crystals to form on your string, or if you put a little piece of wooden stick in there, it'll actually create some candy for you, and rock candy. And you can grow crystals like this with any substance. Ionic substances famously are very easy to do this with because they have such strong attractive forces between the molecules or the particles. So technically you would make a supersaturated solution. Now when you make a supersaturated solution, it has very interesting properties. So here is a supersaturated solution of a substance. Now it looks like water, but there are a bunch of particles dissolved, much more than the solution can handle. So here we have a tiny little crystal that's about to get dropped in. As soon as that happens, instantly the whole thing crystallizes. because technically at this point you can get it to the point where you have 80% of it is actually the solute. You can get it, some substances can get this high, which the solute has overcome the solvent essentially. The solute has become the solvent in a sense. And you can see that here because when the solute comes out of solution, most of it is crystalline. And you usually form these nice big crystals. Very beautiful little process to observe. And supersaturated solution here, it says, is unstable. And so since it's unstable, if you leave it to the open environment for a while, eventually the water evaporates and it'll crystallize on its own. This will happen on its own. But if you catch it before then, you can actually induce this crystallization process at room temperature. And usually there actually is a heat component to it. Usually when this happens, because you're forming a solid, this is actually an exothermic process. It's a fun thing to see, and heating pads, some hot pads, are actually made on this principle. So, not bad. Supersaturated solutions. Okay, let's talk about why some substances mix with others and others do not. So here you have water and oil. An example, a fun little example of oil particles not dissolving. They form these spherical shapes, and then they'll combine together. You have two layers. So why does this happen? And the big saying that we have in chemistry, the axiom, is like dissolves like, which simply means if you're a polar substance, you will tend to dissolve in polar solvents. If you're a nonpolar substance, like oil, you'll tend to dissolve in nonpolar solvents. So because oil is nonpolar, water is polar, oil and water do not mix. And oil is just another reason why oil and water especially exhibit this property of not mixing is because water is a pretty tiny molecule compared to oil. Oil is actually very big. This is actually a small molecule. The real oil molecule has many, many more atoms, usually a good 18 carbons long, so large. And so here we're actually minimizing their interaction in terms of London dispersion forces and in terms of water has hydrogen bonding, and the oil just has London dispersion forces. So these are as dissimilar as you can get almost, and that's why water and oil exhibit this radical property of you cannot mix them at all. And we'll show you some that kind of go in between. Actually, soap is a famous substance that was created, that was formed to be able to dissolve both polar and nonpolar substances. So chemists actually they discovered soap pretty early on. The making of soap is actually considered the earliest chemical reaction available, and what you do is the ancients used to mix sodium hydroxide with fats or oils, and technically what you're doing, this is a very, very ionic substance. This is a very, very nonpolar covalent substance, but the reaction occurs between the two, and you create a molecule which gets you a polar end and a nonpolar tail. They usually call this a head and a tail molecule. And this nonpolar substance will mix with your fats, or nonpolar tail will mix with nonpolar substances like fats, oils, and the polar head mixes with water-soluble substances, dirt, and so forth. And you're able to dissolve essentially anything off your hands, be it oily or water-based. And these molecules actually make an appearance in the lipid bilayer. Remember, cells have a lipid bilayer. It has essentially water-loving and water-hating surfaces to it. So there's a lipid bilayer that looks like this. And the lipid bilayer contains these what are called fatty acids that actually have this property as well. But soap is, it came from essentially these fatty acids. So, very fun substance, a very common substance, but it contains both parts to it. If the substances are miscible in each other, this is another term, just a vocab term. Miscible sounds like mixable. Sounds like you can mix it, and that's, I think, the idea. Miscible, that means the substance completely dissolve in one another. In other words, there is no set limit. They can dissolve in any proportion. A famous example of this is alcohol and water. And the alcohol I'm referring to is ethanol, this alcohol here. Now, what you can do is you can dissolve 10% of alcohol in water and 90% water. you could get 20%, you can do 50-50, 50-50 mixture. You can flip it, you can do a 90-10 mixture, so the ethanol can become the solvent, the water can become the solute. That's what we mean by miscible. There's really no limit. And this usually happens between substances that exhibit hydrogen bonding. So in the case of water and ethanol, and methanol works as well, you have hydrogen bonding. So the ethanol molecule has this OH group to which water can bond hydrogen through the hydrogen bonding in this case. And this oftentimes happens between water and these small organic molecules that have hydrogen bonding in them. These will be miscible. Nonpolar substances can also be miscible. An example of this would be oil and gasoline. Oil and gasoline would also be miscible. You can mix them in any proportion together. So many liquids will exhibit this. Usually it's a liquid and a liquid. Usually a solid has a limit to the solubility in a liquid, and a gas as well in a liquid. But liquids and liquids usually exhibit this property of miscibility. Okay, so another example of solubility in water and how this idea of being similar in your intermolecular forces works. Here we have two big molecules. I'm going to talk a little bit about macromolecules. So here's vitamin A, a pretty big molecule, and here's vitamin C, also quite big, not as big. Both of these are vital to your diet. That's why they're called vitamins. They are vital minerals. So you've got to make sure you have these from the outside. Your body can't produce them. You have to get them from the outside. So make sure you eat yourself some citrus fruit and some non-citrus fruit. So what you've got in vitamin A is very slight solubility in water, so not very soluble. And that's because most of it is nonpolar. You'll see this is the nonpolar portion of the molecule. But you do have a slight polar head, so that allows it to dissolve in water. So essentially, water molecules, H2O molecules, can come up, and a few of them can bond to the. You can do it like this if you like. So a few of these water molecules will come in and bond. Not many though. Not much bonding happening back here. However, if you take a look at vitamin C, you have so many OH groups on vitamin C that water can come in and solvate this thing pretty readily. And so this is very soluble in water. So just analyzing the structure of the molecule, you can actually predict its solubility just from structure. And that's why this rule of polar dissolve polar, nonpolar dissolve nonpolar works so well. Vitamin A, something in biology, this would be important because say if you have some sort of substance that needs to go and sit in between the lipid bilayer of your cell, it has to sit inside this lipid bilayer, which is nonpolar, then you have to make sure the molecule itself is nonpolar. Otherwise it won't sit in there, right? It won't be able to bond. So oftentimes cholesterol, for example, is very nonpolar. There's a bunch of cholesterol between the lipid bilayer. Alright? So let's end up talking about water, which is called the universal solvent. Water is beautiful in its ability to dissolve. One of its most valuable properties is actually this ability to dissolve. It dissolves many things. It can dissolve many ionic compounds, many covalent compounds, sugar, ethanol. It can dissolve macromolecules. So vitamin A, vitamin C is technically not yet a macromolecule. Macromolecules would be things like proteins in the body, and even DNA. These would be macromolecules. And it can also dissolve gases. In fact, the reason why fish can survive is because there's oxygen dissolved in water. And this is why water is the medium of life. Most of our bodies are made of water, and most animals' bodies are made of water. Well, at least mammal-type animals made of water. So water is able to dissolve very nicely. It looks like this is maybe an Alka-Seltzer tablet, or maybe some aspirin tablet dissolving in water. Very soluble. And we have a picture and a little animation of some biomolecules dissolving in water. So DNA, the famous double helix, is very soluble in water, and DNA itself is actually held together by hydrogen bonds. So it has plenty of hydrogen bonding going on, especially down here. These are held together by hydrogen bonds, but it's a hydrogen bonding type molecule, and so are proteins. Proteins famously have a lot of hydrogen bonding going on. So look at those fine molecules, water molecules dancing around, solvating the protein. So, and proteins are what run our bodies, and so our bodies are based on the solvent water. Very important. Now, let's talk about the solubility of gases just slightly. what we say is polar gases are very soluble in water. So polar gases being like HCl, ammonia has hydrogen bonding, but even something like sulfur trioxide, because it is polar, nope, sulfur trioxide is non-polar. I meant to say sulfur dioxide. Sulfur dioxide is very polar. Now sulfur trioxide is also soluble in water, but sulfur dioxide is polar. Trioxide, if you draw the structure, trioxide is actually non-polar. But even non-polar gases dissolve in water. Now they have a slight solubility in water, but the bigger the molecule, the more soluble it is. Now we know that O2 must be soluble in water because fish breathe O2. This fish has a little trouble breathing O2. CO2 is much more soluble than oxygen in water. And we need this because we have green life, like plant life, that needs to breathe the CO2 underwater, and that plankton and so forth. And that happens because CO2 is dissolved in water. Now, what happens is the bigger the gas, the nonpolar gas, the more soluble it is in water. So it can actually dissolve using its London dispersion forces. Since water does have London dispersion forces, and something like CO2 has London dispersion forces, the two can actually combine together and dissolve. Not a lot of CO2 gets dissolved in water, but enough for it to be significant for us to measure. And the larger the molecule, the more soluble it is in, usually the gas, the larger the gas, the more soluble it is in water. That's the idea. Okay? So let's do a few example problems and we'll call it a lesson. So here we're simply asking which of the following will dissolve in one another. And the rule is, if you're polar, you'll probably dissolve more in polar substances, and nonpolar will dissolve in nonpolar. So which are polar, which are nonpolar? Well, this one here is polar. This is nonpolar. Evenly dispersed, remember, is nonpolar. This looks like nonpolar. This is cyclopentane, nonpolar, liquid. And this is good old methanol. This is a polar liquid. So your polars will dissolve in each other, and your nonpolars will dissolve in each other. And that's the idea. Simple as that, really. The second example problem does the same thing, except now it gives you formulas instead of drawing the structures out. So you have to kind of look and see if you can visualize the structure. The question is, which is more likely to dissolve in carbon tetrachloride, CCl4, and which is more likely to dissolve in water? So water is the polar one, carbon tet is the nonpolar one. Well, here we have HCl. HCl is polar because you have two different sides to the molecule. So HCl will dissolve in water. What else can dissolve in water? Well, here we have an ionic compound, sulfate. Sulfate is actually very soluble in water, so it also dissolves. So ionic compounds will dissolve in water. Ionic compounds have charges to them. Water has a partial charge. That's what the dipole business means, like partial charge. And so the other two, iodine is nonpolar, so it'll dissolve in the nonpolar substance. And C7H16, this is called heptane, it's an organic molecule, will also dissolve in the carbon tetrachloride. C7H16 has 7 carbons, essentially, and then all around it, it has hydrogens, 16 of them, 2 on each carbon, and then 2 more at the end, and that's how you got the 16, and that's why it's nonpolar, and that's why it's able to mix with carbon tetrachloride, and that's the idea. Now, to finish up, carbon tet could be slightly soluble in water. In fact, you can probably read and find out that carbon tet could be slightly soluble in the water because they both have London dispersion forces, and the solubility between them is, is enough where you can measure it, but nothing like ionic compounds, nothing like polar compounds. And so that's it. All right, this wraps up video 2 of Unit 8.